Yeah. Good morning, dear students. Today we will discuss binary search tree from where we left off in the last class, rather, right? So, as we have discussed, I hope all of you can see my screen. Is my voice audible?
Yes, sir.
Yes, my voice is audible now. Yeah, fine. So, binary search tree. Okay, what is binary search tree basically? It is a tree wherein you have a special node called root, and the left subtree to the root will have the values lesser than the root, and a right subtree of root will have values greater than the root, right? And this particular property is going to be recurrently applied on every particular node. That means that every node over the binary search tree is again a binary search tree, right? And let us take some values, a sequence of values starting with 10, 5, 20, 15, 8, 12. Then how do we insert over the binary search tree, right? What is the mechanism behind? So for which we have discussed the algorithm, right? To create the binary search tree, we need about 4 pointers. I'm taking p, root, cursor, and parent. P is the pointer with which I'll be holding the newly created node, rather, right? And root is going to point always the root node of your binary search tree, right? That is a point from where you start doing any kind of operation on the binary search tree, whether it could be insertion, deletion, or searching, and all kind of thing, right? And cursor is another pointer we have taken in order to move across the scan forward the binary search tree in order to find the parent here. Right, parent is another pointer with which we can hold the parent address of the newly created node. You know, so here in insert algorithm we have seen, we are just first creating a new node, then we're making its left and right pointers are null, and the key which you're passing are the data which you're passing to the insert algorithm. You're assigning it to the data of the p pointed node, and then initially root is null, so when the first node is created, obviously that will be pointed by root. But the subsequent nodes, for the subsequent node, this condition is going to be false. You go to the else part. In else part, you can see the cursor is starting from root and then fetching you the parent with the help of this particular while loop. So in this while loop, while cursor is not null, what you're saying, parent equal to cursor, and then you say that if pointer p pointer data is less than the cursor data, then you're moving cursor to the left, otherwise moving cursor to the right. That way, when you come out of the loop, you are able to hold the parent address in the parent pointer. Now you're going to attach your new node, that is p, to the parent either left or right by comparing its data with the parent data. If it is less than the parent data, it will go to the left, otherwise it goes to the right of the same. Okay, duplicate data are not allowed over the binary system, for which you have written another case here, rather, right? So this is how the insert algorithm in iterative manner going to be implemented, rather, right? Now coming to the deletion of the same, if you are deleting, right? So deletion, when you are performing on the binary search tree, I can classify it into different cases. Case one is the node which you are deleting is a leaf node, right? If the node to be deleted is a leaf node, then what will you do, right? Like in this case, the tree which you have constructed, like say for example 8 is a leaf node and 12 is a leaf node, rather, right? So when you are deleting the node which is nothing but a leaf itself, then you can simply delete it by making the pointer value of its parent as null. See, 12, if you are trying to delete, let us say 12, in that case the 12 is attached to the left pointer of 15, right? So when you delete this, then the left pointer of its parent should be null. That has to be taken care, rather, right? Okay. Like in case of 8, if you're deleting 8, 8 is attached to the right pointer of 5. So you have to make its parent right as null, then delete it, rather, right? So this is one solution. This is the first case which I have probably have to include in my delete algorithm. Basically, when you're deleting, when you're designing the algorithm, you must have to analyze the algorithm. You have to analyze the problem and then identify the different cases that you may encounter with that particular analysis rather, right? So based on the different cases, you're going to suggest the different solution for the same. That's how the algorithm is going to be designed rather, right? So the first case that I'm considering here when I'm deleting a node is node to be deleted is a leaf node. If node to be deleted is a leaf node, then what you have to do is uh, you have to place the null value in its parent associated pointer rather, right? So before deleting the node, make the parent pointer value null. That means if let us say your leaf node is, in this case I get two sub cases rather, right? Sub cases one, that is if leaf node is left of its parent, then what is that you have to do? You have to make the parent left as null. Then make parent left as null. Yes, son. Under this subcase 2, I can say if leaf node is the other way around, if the node to be deleted, the other way around, right? If node leaf node or node to be deleted is right of its parent, then make parent right as null and then delete it, right? And now another case, that is case 2, if the node to be deleted is having either left or right child, either left or right child, then what do? Then attach its child to its parent, to its parent, and then delete it. Okay. Okay, that is in this case, case 2. I'll explain you with this particular tree here that we have. You can see here, if you are trying to delete, let us say 15. When you are trying to delete 15, 15 is having left child. Then what do you have to do? You have to attach its left child to its parent. It means this 12 has to be attached to the left of 12 and then left of 20 and then delete 15. Got it? Let us say if you are trying to delete 5, 5 is having its right child, then this right child has to be attached to its parent rather, right? So this 8 has to be attached to left of 10 and then you have to delete 5. This is the case 2. I hope you understand, right? So now coming to case 3. Case 3, that is the node to be deleted is having both. Node to be deleted is having both left and right child. Okay, these are the possible cases that you may encounter with, rather, right? One is you don't have left and right child, that is said to be the leaf node, right? So when it is a leaf node, you simply delete it. Before deleting, you need to make its parent pointer as null value. That is the first case. Then case 2 is if the node to be deleted is having either left or right child, then make its parent pointer as attach this left or right child to its parent and then delete it, rather, right? That is case 2. And now coming to case 3, when the node to be deleted is having both left and right child. Okay, that is in case of, let us say for example, in this tree, when you take under case 3, if you are trying to delete 10, 10 is having both left and right child. In that case, what you have to do is you will have to find, you go to the right child first and take the minimum out of this right child. Okay, so when you go to the right child, you have 20 and minimum out of this particular tree is nothing but 12. Then you are going to exchange this minimum value with the root. Okay, it means 10 is going to be swapped with 10 is going to be replaced with this 12. And then what is that you're going to do is you're going to delete this 12 from here, rather, right? That's how you make it. Because when you delete, after you delete, you have to ensure that the property should not be violated. What is the property of the binary search tree? Left should be less than the root and right should be greater than the root, right? So if I bring this 12 over here, I don't think you have any issue, right? So that's how the solution is. What is that we're going to do is we go to its right subtree. From its right subtree, we'll be finding the minimum out of it. Minimum in the sense leftmost node value, rather, right? So then get the minimum out of the right subtree, which is to be taken as for replacing the node which is having, which is not, which is to be rather really deleted. Got it? So the node to be deleted is going to be replaced with what? Node to be deleted is going to be replaced with the minimum of its right subtree, and then that minimum is going to be rather deleted. That's how apply the solution, right? So what is that you're going to do is find minimum in the sense leftmost node of the right subtree. Leftmost node of right subtree, replace node to be deleted with this minimum value and delete that minimum. Okay, this is the solution. This is the solution. So now let us take that example here. Now I want to delete under third case. I am taking 10. When I am deleting 10, what is that I have to do as per the third case? Because it is coming under the third case, it is having both the child, left and right child. When a node to be deleted is having both left and right child, you find the leftmost node of its right subtree. The right subtree is this one, and what is the leftmost node of it, which is nothing but 12. So this 12 has to be replaced with this 10. So it means when you are deleting 10, what is happening is 10 is going to be replaced with what? 12, and this 12 is going to be deleted. This node is going to be deleted. The remaining is intact. Okay, remaining doesn't get changed, rather, right? So you can see here, uh, is it after deletion of this particular 10? Okay, Are you able to see the node is violating BST property? No. Root is 12. Left of it is having lesser than it, and right of it is having greater than it. So no issue, right? This is how the delete algorithm has to be implemented. So taking these three cases into consideration. So while you're deleting, what is that? First thing you do is you need to first search for that particular node to be deleted. If it is available only, then you go for deletion, right? For deletion, the precondition is you need to search and you need to ensure that that particular node which you are trying to delete is available on the particular binary search tree. Then you can go for deletion. So now when you are trying to delete, you may encounter with these three cases. It means that you need to have the solution for all these three cases to be fixed in your algorithm. Only then your algorithm will work in all possible cases. So first case which I've identified is the node to be deleted is a leaf node. It means it doesn't have any left child or right child. Okay, like in this case, if you are trying to delete 12 or 8, they are the leaf nodes. When you are trying to delete the leaf node, then what is that you have to do? You have to make its parent pointer as null. See, parent left is held with the address of this particular node rather, right? So now when you are deleting this, that has to be null. Similarly, if you are deleting 8, which is a leaf node coming under case 1, if you are deleting this, then it is attached to its parent right. So right pointer should be null when you delete this. So this is what exactly you are going to do in case 1. In case 2 is when the node to be deleted is having either left child or right child. For example, if you are trying to delete 5, is having right child. If you are deleting 15, is having a left child. So when you having either left or right child, what is that you are going to do to provide the solution under case 2 is you are going to attach its left or right child to its parents and then delete it. So for example, if you are trying to delete 5, then what is that you have to do? You have to attach its right child to its parent and then delete it. Similarly, if you are trying to delete 15, let us say it is coming under case 2 itself. Okay, then what is that you're going to do? You will be attaching its right child to its parent and then deleting. This is case 2, right? And the case 3 is the node when you are trying to delete is having both left and right child. In case of, let us say for example, 10 you are deleting, is having both left and right child. So in that case, what is the solution? Under case 3, the solution is find the leftmost node of the right subtree. Okay, which I am saying the minimum of its right subtree rather, right? So when you go to its right subtree is 20. In that right subtree, what is the leftmost node is in the number 12. So now replace this node to be deleted with this particular minimum value. That is nothing but minimum of its right subtree or leftmost node of the right subtree. Then delete that particular minimum node. Then your tree becomes like this. Okay. So again, by being able to satisfy that by BST property, we are able to provide the solution for all these particular three cases rather, right? Now we can let us look at the program that we have already written for the same. I hope BST is clear for all of you. Yes. See, unit wise course material I have already published in the classroom. Okay. Let us look at the program here. Today is a lab, so you please execute these programs for today's lab. Yeah, by today evening I'll give you the assignment questions. You prepare those. Huh? Yeah, you can see here binary search tree, binary search tree program. So we have a tree node. We have taken a self-referential structure for representing the node having data is one field, another two pointer field left and right field to hold the address of the left and right subtree. The find minimum is going to find the minimum in that particular subtree. It's nothing but leftmost node of the same, rather, right? Max will give you the rightmost node of the same. Fine. So then you have an insert algorithm that I have discussed as iterative manner, but this is implemented here with the help of the recursive manner, right? So first you create a node, you can see. Okay. First, you create a new node here. First, you create a new node with the help of new in C++. In C, you'll be using malloc. We are implementing it using C++, so use this. I have put this in comment anyway. Now, next is you're making both of its left and right as null, and the data which you passed as an argument to insert has been placed into its data field of the newly created node, which is being here pointed through temp pointer. Okay, and then you're comparing the data. If the data is greater than the node data, node is nothing but the root value initially. Fine. So if it is null, initially it is null, so that is going to be attached, that becomes the root rather. But subsequent onwards, what happens is going to be compared. So if the data is found to be greater, then that you will be calling the same algorithm recursively by passing node right. It means root to move to the right of the same. Fine. If it is less, then the root move to the left of it rather, right? That's how exactly these recursive callings. This is said to be two-way recursion rather, right? Left recursion and right recursion. So with the help of two-way recursion, we have implemented this. Of course, the same iterative, one which I have already explained with the help of example before rather, right? So then it finds for its parent, and once it gets the parent, then it iterates, right? That's how the insert algorithm works. Now coming to the delete, as I've seen, there are three cases has to be taken care. So here, this delete algorithm is again implemented using the recursion. So you are passing the root and the data, right? So you first take a pointer temp which you start with root, and you can see here node in, if the root value is null, it means there are no elements at all. Then you say element not found. But the data which you have passed as an argument is going to be compared with the root data. Node in the sense here is nothing but the root, of course. If it is lesser than the root data, then you need to call the algorithm by taking the root to the left of the same, or else you have to move to the right. This is how you are performing the searching the other way around, right? In order to delete the element, first you need to search and ensure that it is available on the particular binary search tree. So with the help of this mechanism, you are first of all searching for the particular node. Once it is ensured that the particular data is available, then what is that you're going to do? You are directly checking for the third case. This is the third case, you can see, right? When both right and left pointers are available, it means when the node to be deleted is having both left and right subtree, then what is that you're going to do? By going to its right subtree, finding the minimum of the same. Okay, that is what exactly I've done, right? Then you replace the node is nothing but the root data, the node to be deleted rather, right? So the node data has to be replaced with this minimum rather, right? Which you have held it through temp, right? Now then, what is that you want to do? You are going to delete this particular minimum, calling the same, passing this temp data. Temp is nothing but the minimum, so which is to be deleted rather, right? That's how the case 3 here is implemented, you can see. And now coming to the remaining two cases here have been adjusted in this particular else, you can see. So if the node is having only right, left is null means only right is there. When there is only right, then you just attach the right to its parent, and then delete it rather, right? So if it is having only left, then left has to be attached to its parent, and then free temp, right? Free temp is being used in what do you call C and C++, you said delete node rather, right? So that's how you delete it. This is a find algorithm to search for the node whether it is available or not, which has already been part of your delete algorithm you have seen rather, right? So and then to traverse, when you are traversing the tree, you can traverse in three orders: in order, pre-order, post order. In order, how do you traverse? You first go to the left. Yes or no? You first go to the left, and then you traverse, then you go to its right subtree. That is left, right, and root. So if you traverse in order, it will print the elements in ascending order. This is one kind of what do you call sorting technique. We call this sorting technique as tree sort, right? If you create a binary search tree and apply the in order technique that is said to be tree sort. It is also taking the time complexity of about n log n rather, right? Okay, so now similarly you can see here you have pre-order. In pre-order, what you do, you will first traverse the data, right? You first traverse the root, right? Then you traverse the left subtree, then you traverse the right subtree. Okay, so that you could have seen here rather, right? Then in post order, what do you do? You will first traverse the left subtree. You can see first you're traversing left subtree, then you traverse the right subtree, then you traverse the root data, right? So that is left right root. Okay, so in the main we are trying to implement all these functions here. You can see uh, initially, as I said, root should be null before you go for any function of this to be rather called or implemented, right? So root is null initially. Null is a constant identifier, right? Whose value is equivalent to zero rather, right? So now with the help of this infinite loop, we are first displaying a menu, one for insertion, two for deletion, like that, for which different cases you have based on the choice that you are going to input here, right? You have implemented with the help of that, with the help of a switch case. So this switch case, okay, so when the choice is taken as one, you go for insert. So enter the element to be inserted. The value which you insert rather, right? That value will be passed with root. Initially, root value is null rather, right? So that newly created node becomes root. But subsequent insertions will be inserted to the root either left or right based on the value of that root when being compared rather, right? As per the BSP property. Just how, and then you want to display the same after immediately inserting with the help of in order route, you are traversing and then showing what all the data available till that time. And when you are entering two, when you are taking the choice as two, then it is performing delete operation here. You can see the delete. While you're deleting, the element to be deleted must be available on the tree first, right? So the data which you have given first, it will search for it. If it is available, then it will delete the same. And then after deleting whatever the leftover elements, you can probably display it with the help of in order. Then in order traversal for case 3 we have in order travel to display 4 pre-order, 5 post order, and 6 find min, and 7 is find max, and 8 is such kind of thing, right? So based on the different choices here, we are calling the respective functions and then we are implementing. So when you execute this, compile it with the help of G++. If you are implementing it in Linux, then you when you execute, how do you execute that slash a dot out? You will get the menu like this in based on the choices, the different kind of operations you do perform, and then you get the output like this. So I hope this is clear to all of you. Yes, please, yeah, please execute this program, and I'll show you with Linux. If you have it, if you have Linux at home, you can probably execute that in your Linux. Or else in online GDB also you can, but sometimes due to space issue, because you have pointers here, it may result some segmentation fault. But you can try once. I would like to execute the same in Ubuntu. So, To start Linux, it takes time. I'm having a virtual machine installed on my system, so it takes time. Yeah, I'll open the terminal here. Let us increase the size. This is BST program, BST ADS, right? For ADS dot CPP. Okay, BST ADS dot uh, Shift Control V. Now let me copy the remaining. Control C. Okay, the next page from here it is. Let me copy this remaining part. Control C, Shift Control V. Okay, so I have copied this program and let us compile this. Yeah, there are certain errors, of course. Uh, yeah, these are all with, I think probably my input output issue. We'll solve it. Go back to the program. Hash include IO stream using namespace std node string find me. If data here hyphen is missing actually. Here, escape a Should go to the append mode, right? First, escape I'll say. Otherwise, insert mode. I'll do one thing. Control A. Let us take this first. Let us take this online compiler also. We'll do simultaneously. Control C. Control V. Control V. Take the next page code. Control C. Control V. Take the next page code. Control C. Control V. I'm taking simultaneously at both the places to execute it. We'll see. Let's choose the language as C++ here. Run this code and see. Yeah, here it is running good. Okay, you can see it's giving us the menu here. Insert, delete, in order, pre-order, post-order, find min, find mix. Search, exit. Enter your choice. Let us say you go with one. So enter the element to be inserted. Let us say you can insert the same way if you want to go with rather, right? This is the order you have given for this particular binary search tree. You want to create binary search tree of this kind where 10 5 20 15 8 12. Okay, so you want to go with it. 10, then again you insert. You can see there is an element 1, that is 10, and again I am inserting one more, 15. Okay, it is showing the in order traversal. In order traversal you get the elements in ascending order rather, right? Then again enter your choice with 1. I have said 10 15. Let us take 12. Again, now you can say 8 element to be inserted. We can see the elements are being here printed always in the ascending order because it is traversing in which order? In order. In order means ascending order, right? Left, root, right. Left is always lesser than the root, then root, then the right side are greater than the root. It means they are printing in the order of left, root, right. It's nothing but ascending order, right? So you can see now you want to insert one more element. Okay, 8, 10, 12, 15, and now you want to insert, let us say, 20. So you can say 8, 10, 12, 15, 20. You want to insert one more element, let us say 5. So your tree is having 5, 8, 10, 12, 15. Now you want to traverse it in pre-order and see, right? In pre-order, what happens? Pre-order to traverse, we have fourth option, right? Enter your choices four. See, when this tree is constructed, what is the root actually? See, here it is traversing in the, when it is traversing in the pre-order, it is nothing but root. What is the root here? 10. 10 is the root rather, right? Then you have at the left side you have 8, 5. Yes or no? The same sequence I have given, 10, 5, 20, 15, 8, 12, right? So you can see this is how the tree is. So in pre-order, when you traverse, what happens? First it will traverse the root, or then it traverse the left and then traverse the right. 10, 5, 8, then you can see that's how exactly it has traversed or not. 10, 8, 5, and then you can see 15, 12, 20. And if you want to traverse post order, then this root print value will be at the end, you can see rather, right? Post order is 5 here, choice is 5. So you can see 10 is at the end. Are you able to see 10 is at the end? Yes, right? You want to find the minimum of the same. So with the help of 6, right? You can find the minimum. What is it? 5. You want to find the maximum of the same, you press 7. You will get the maximum of it rather, right? It's nothing but 20. So you want to search for a particular element. Let us say you are searching for some which is not available. For example, uh, choices for search is 8, and okay, so that's how exactly it's working. You can probably delete again and then see it works for the same. Okay, give the elements and then delete. What is the sequence? 10, 10, 5, 20, 15, 8, 12. 10, 5, 20, 10, 5, 10, 5, 10 I have. So 10 will not be inserted rather, right? Duplicate elements will not be allowed. Here you can see I have inserted 10 before and again 10. What happens? You don't have, you don't have duplicate nodes to be allowed rather, right? So that 10 will not be inserted. Duplicate node will not be inserted. So 10, 5, 20. Then and we have 15, 8, 12. Okay, 15, 8, 12. 15, 8, 12. Okay, so this is how your tree is: 5, 8, 10, 12, 15, 20. 10 is the root rather, right? Now we want to delete some elements. If you are deleting, let us say, third case, that is 10, root itself, root is 10 here, right? Let us go with the third case. When you are deleting 10 itself, right? It is nothing but the root. Then who will become the root? The minimum out of it. Minimum is out basically 12. So that 12 will become the root, you can see, right? You got the element 5, 8, 12, 15, 20. In order to know whether 12 is root or not, you just go with the pre-order traversal, because in pre-order you get the root value at the beginning rather, right? So just go with pre-order traversal, you will understand. You can see 12 is the root. Yes or no? Did you understand? Yes. See, when you are deleting 10, who will become root 12, right? If the tree is like this, right? That's how the mechanism is applied rather, right? I hope this is clear to all of you. All of you are able to follow it. Yes? Please respond. So, yeah, similarly, you can look for any other third case or second case. I want to delete one more element. Choice is 2. Now, let us delete after your tree has become like this. Okay, you want to delete, let us say, 20. When you delete 20, what happens? This 15 go and get attached to the 12's right. Yes or no? If you are deleting 8, then of course the 5 right will be null. And if you are deleting, let us say, 5, then 8 will go and get attached to the left of 12. That you can probably see. I delete 20 here and then see. We'll delete 20. Now you can see 5, 8, 12, 15. Who is the root? Root is 12, 12 itself. Still root is 12 only, right? 12, 5, 8, 15. Okay. Because on the right side you will have only 15 to the 12. And the left side you have 5, 8 rather, right? So you want to know to the left of root who are there. You can probably traverse it in order. You will understand it, right? You traverse it in order. In order is 3, right? So you can see to the left of 12, that is root, you have 5, 8, and to the right you have only 15. Yes or no? When 20 is deleted, now 15 was actually the child of 15 was actually the child of 20. So when 20 was deleted, 20 has taken the responsibility of its child to give it to its parent, and then it gets deleted rather, right? That's how exactly is happening. So to the right, when this is deleted, only 15 is left on the right of 12. Okay, that's how exactly you can see here. 12 is the root, so right of 12 is only 15 after 20 is deleted. That's how, for example, if you are deleting the leaf node, in this case, what is a leaf node? After you delete this, 15 is a leaf node, of course 8 is also a leaf node. So when you delete leaf node, then the right becomes, say for example, if you are deleting 15, then you don't have right of 12 anything. I'll delete that leaf node and then see 2. Okay, I am deleting, let us say, now 50. Then what will be the right of root? That is, root is 12, of course, right? Right of root is null. You can see only left is available. Okay, that's how exactly all three cases are being taken into consideration and they are working fine. Right, I hope you have understood this. You can probably run this program opening online GDB compiler on your system, or through your mobile also you can run this, right? I have done it through online compiler only, not through Unix, right? No, Unix also we can run properly. That some issue I'm finding. I'll probably resolve it afterwards. But then you can see here, I have executed it on your online compiler. Just open it with online GDB. Open an account on this compiler with your official mail ID, and then you can create a new project and run all the programs that will be available for online. You can view it afterwards. Also, you can I can view your programs if you share that link. Okay, so I want you to do this all programs executed on this online GDB compiler. Okay, so this is clear to all of you. I hope you can execute this program for today. You execute till here. I told you to execute stack use linked list in before lab. So today's lab you are implementing this BST. Okay. So probably next class we'll discuss about AVL tree. So your syllabus for first internal will be till AVL tree. Okay. Tomorrow I will discuss AVL tree. So 2.5 unit will be there. So if you go to classroom, I have here published the syllabus, I mean material, course material of all your 5 units. So course unit one consists of hashing. I have discussed this, of course, before, right? Quadratic double hashing as well are there. There are two PDFs. One, so you can find the required material in these two PDFs. In unit 2, skip list material is you know available here. Notes of the same, which I have discussed, of course, taking the same examples in the PPT. So go through this unit 2 as well. In unit 3, uh, you know, binary search tree and AVL tree. These two I will be having, right? The first two. Probably this AVL tree I'll discuss tomorrow. Binary search tree, I hope it is clear in today's class with deletion, insertion, all traversals, and search operation with min max rather, right? So we have left with few more topics in unit 3: v trees, red block trees, and split trees, memory trees. This probably will discuss after the first internal. So in first internal you will be having first 2.5 units, right? First 2 units plus these two topics in unit 3. This comes to 2.5 unit. In unit 4, we have string pattern matching algorithm, LCS problem, and tries, and of course Halfman coding and all. That material is published here. We'll probably discuss afterwards. Okay, and then in unit 5, you have you know quad trees, computational geometry, and KD trees and all. So this is also published here. Anyway, you can go through the material uh, before the class as well, which will help you to understand the class a little better. Fine. We'll stop here for now.